Hey everyone, it's Ken. What I want to do in this video is head towards the definition of the definite integral. And the way that we're going to do that is I want to show you the most general way to approximate the signed area under or above a curve. What we've done so far, we've looked at the left endpoint approximation, the right endpoint, and the midpoint approximation. And what these things have in common is that you take your interval and divide it up into subintervals of equal width. The way that they're different is in each of those subintervals, you choose a different point to give you the y value. So you could choose the left endpoint, the right endpoint, or the midpoint. But actually, you can really choose any point you want in each of these subintervals to give you a y value in like the respective subinterval. And you'd still get an approximation that's different. Even further than that, you don't have to choose subintervals that have equal width. You could just choose any partition of the interval from A to B. And maybe they don't have all the same width, but as long as those subintervals are getting smaller and smaller and smaller, your approximations are still going to get better and better so long as the function is continuous, for instance. So I want to sort of codify all of that into a new, more general way of approximating area. So I'm going to give you a formula that encapsulates left, right, and midpoints, among many other things. So the way that I'm going to set it up is instead of first splitting up into equal subintervals, I'm going to say what I mean by like a partition. So say we're starting out, I'll draw a graph first. Say we're starting out with some function from A to B, defined on an interval from A to B. This is y equals f of x. And you want to subdivide this interval into subintervals somehow. And so what you'll do is with what we call a partition. I'm going to say P for partition. So a partition is just a collection of points, x0, x1, all the way up to x sub n. So it's n plus 1 points. And it has the property that the x0 has to be equal to a, like usual. And xn has to be equal to b, like usual. And then x1 should be bigger than x0, x2 should be bigger than x1. So they're increasing, so they really can be endpoints. And I might, for example, label them here. Here's like x0, then 1, 2, 3, 4, 5. So they're closer together. Here it's a little farther apart, 6. So maybe that's like the location. And once you choose those endpoints, that gives you a partition of the interval from A to B into n subintervals, and you can see them there. And the ith subinterval goes from xi minus 1 to xi. And the width of the ith subinterval, that's called delta xi. Before we used delta x, when the widths were all the same, here where they could be different, I actually have to say delta xi, and it's defined to be xi minus 1. That's just the length of that subinterval. And as we're heading towards making the approximations better and better, for each partition you pick, you'll get a different, ultimately, approximation. So you're going to be concerned with the distance between individual points. In other words, you're going to be concerned with actually this delta xi. And in particular, you're going to be wanting that delta xi to be pretty small. And so the way we're going to keep track of that is I'm going to say the length, or you'll hear it called width. You'll also hear it called mesh, mesh of the partition. It's just going to be the smallest of all the delta xi's, so the minimum of maybe delta x1 all the way up to delta xn. So in this picture, maybe that length is the mesh or the width of the partition. Okay, and so now how do we choose the y values? Well, you could do left endpoints, you could do right endpoints or midpoints like before, but you could really do anything. So what I'll ask you to do is for each interval, choose a number, call it Ci. So you're going to choose C1, C2, C3, all the way up to Cn, n points for n intervals. And each Ci has to be bigger than or equal to I minus 1 and less than or equal to xi. And I'm going to collect them all together in a set and call it C for C1 to Cn. And you could pick them however you like. Maybe I'll sort of just pick some points randomly. That could be C1, maybe C2 over here, 3, 4. So you get the idea. You can choose these points wherever you like. So you've chosen n plus 1 endpoints to give you n intervals. And then for each interval, you've chosen a point somewhere. And now we can go to town. So now we can take the associated point, walk upstairs, and collect the y value. And then that's the height of our rectangle. So over here, I see the y value, maybe like right there. Something like that. And you get the idea. And I could keep on drawing them. I'll draw like one more. Go down here to get the y value. So the rectangles could be these expressions could be negative. We're adding them up to get an approximation of the signed area. And so now what we do, if we want to follow our model for like the left hand or right hand or midpoints, whatever, we're going to be taking the sum. I goes from 1 to n. And so the height is always f of Ci, right? Because whichever point you pick in that ith interval, when you walk upstairs, that's f of Ci. That's what you do. And then, so that's height, and then the base is always given by the width, which is now delta xi, which has this formula. And then you're just adding them together because there's n terms. So that's the most general way to give an approximation of the area if the function's non-negative, or signed area if it crosses the x-axis like that. And this has a special name. It's named after Bernard Riemann. This is called the Riemann sum. And you'll also see it notated R for Riemann. So Riemann sum needs a function. It needs a partition. It's a collection of the endpoints. And it also needs a collection of points C1 to Cn that you chose. So it depends on three things. You fix a function. You choose a partition to get your widths for the base. And then you choose these sample points C1 to Cn in each subinterval to tell you the height. And so as special case of that, the left-hand approximation, the C1 would have just been x0, C2 would have been x1, Cn would have been xn minus 1. So this is what's called a Riemann sum. It allows us to approximate the signed area below or above a curve.